Move you guys over here. It looks like I am recording. So first thing I'm going to start with is one of the things that we didn't talk about under forces. And I do want to come in and talk about it. It's a little different. And one is related to springs. And we can start out with a spring. And the spring will have an initial length L. And then I can hang a mass off of that L. And what we know is going to happen to our spring, it's going to stretch out and it'll have a new length. And then we have our spring comes off of it like this. Now, if we were to plot this, and we were to plot force versus stretch. So if I increase the force, my stretch actually increases. Unless it's a rubber band, or unless we deform the material. But for spring, we usually get it, and we get behavior that looks like this. So this is our force versus stretch. Now, this tells us if I'm going to write the equation for this graph, force is going to equal the slope times my stretch. And this force, if we look at that slope, because this is related to a physical object, we're going to use a K, and this is going to be known as a spring constant. And then my stretch is my length minus my initial length. And this gives us something that we call Hooke's law. Now, Hooke's law isn't there because there's something that's missing in Hooke's law. And we have a negative sign in Hooke's law. And the negative sign comes from that this is a restoring force. My spring is wanting to return to its original shape. But if I'm plotting, especially if I've got a system like this and I'm putting the mass down here. So this is my force due to gravity, which is going to equal my weights, and that will have it draw down. So my spring comes in there, and we can actually measure these spring constants. But it is a restoring force, and that's why when we usually see Hooke's law, we usually see Hooke's law written this way. And its force is equal to this, where this is my stretch, and that's defined as L minus L initial. And this, the reason the negative is there is that the force is wanting to pull back up, and I want to make sure that I get that piece there. So if I've got forces in newtons, we're going to do the absolute value here. If I do the absolute value, I don't have to worry about my negative, and this deals with our magnitude. But I get my force in newtons, then I get this constant here, and this is in meters. So my spring constant is usually written in Newton meters. And if we look at our springs, we get different kinds of springs all the time. You get your spring in your pen, you get the spring around your shock absorber in your car, you get a variety of different things. But this gives us our Hooke's law that we can work with. So let's calculate a spring constant. So I'm gonna start with a spring. And I'm gonna put we'll give it a 250 gram mass. The initial length of my spring was, we'll say, 5 centimeters. But when I put my 250 gram mass on, my new spring length is going to be 15 centimeters. We want to know what is the spring constant. So we'll do that. So my force, the magnitude of my force is going to equal the magnitude of the spring constant times my stretch. So this is going to be K, and this is going to be 15 minus 5. So this is going to give me 10 centimeters times my spring constant. But my force is going to be my mass times gravity. So this is going to be 0.25 kilograms, 9.81 meters per second squared. So I need to convert that to meters. So that's going to be 0.101 meters. Then I have my spring constant. That's in newtons. So I'm going to have 9.81 times 0.25 gives me 2.4525 newtons divided by 0.1 meters, and I'm going to get 24.5 Newton meters for my spring constant. The reason we want to look at this is what we're about to do, and this is a great time to start thinking about how we're going to move something that's a little different. I wanted to plot this graph here because if we look at the area under this graph, the area here has physical meaning. And that physical meaning is actually called work. We're going to get a concept called work. And if we look at the area under this graph, the area under this graph is going to be kx squared divided by 2. That's kind of an interesting factoid here. So we get this area and we're going to define this weird thing called work. And we really want to look at that, but we'll come back to that. But I wanted to show you that the area under this curve actually has physical meaning. So let's start thinking about what happens here. So what we've talked about so far is we've dealt with inertia. And that's our idea that it requires more force. Force has to increase if my mass increases. So in order to get this to move, my force has to increase if my mass increases. If I want to stop a mass that's moving, I'm going to have to apply more force, because we also have our idea that an object in motion or at rest remains that way unless acted upon by an unbalanced force. So we have that idea. The other part of the thing is we know that force is a vector. And the force is going to move in our area vector of acceleration. So let's think about this for a second, because we do this all the time. And one of our homework problems was this. We had a lady pulling on a suitcase. And that lady pulling on a suitcase caused us to do two things. We had the force in the X direction that was allowing my suitcase to accelerate in the X direction. And we had a force in the Y direction. And if I looked at that, here was the weight of my suitcase. Here was the normal force being applied. So I had my normal force. And then I had a little bit of this Y force that was pulling up on my suitcase. And if we think about that for a second, everything that I am doing is not accomplishing the goal. The goal is to get my suitcase to move in that direction. So this part of this doesn't do me any good. Other than it makes it easier and I'm not having to be directly in line for this idea. So that's kind of an interesting aspect that's happening. Totally interesting aspect of what's going on. And so we come to my favoritist definition of physics. Energy is the ability to do work. Normally, when I first write this definition down, doesn't mean anything. We know we've got the words there, but nobody's home because we don't really have a good handle on what work is. But if we look at our situation, which we had in the original situation, which was our suitcase, but let's look at our shopping cart. So if I apply a force here to my shopping cart, our idea is to get my shopping cart to move in that direction. But we also know that I have a thing called the center of gravity. Which we've talked a little bit about. Oops, I can't spell today. And if I'm applying a force up here, I got this weirdness that's happening down there, and I'm not getting the best bang for my buck. And I think we even talked about the fact that if I wanted to move a very large object, and here's its center of gravity, if I apply my force up here, I could get the potential for this to tip over. Or if I apply my force down here, I could have a potential to have it rotate like that. Now, that may or may not be what I want, but the best option is to apply my force right in line with the center of gravity, and I get the most bang for my buck. And this comes from the idea that work is going to be defined as my force, and we're gonna use a dot here, distance. But the thing that's about to happen here is by using this dot product, we also call it a scalar product. And what happens is we lose the vector character. This is no longer going to be a vector. So while we're defining it with this dot product, it's no longer going to be the vector carrier. So let's go back and let's look at our suitcase problem or our shopping cart problem. So I've got some sort of box here. I'm going to apply a force, and I want my box to move along this direction, and we want to move it along a direction D. This is force, and we want to move it along a direction D. Well, the force that's going to do what we want it to do, if we look at this angle, the magnitude of my force that's in line with, then I'm all in line with this, is going to look like this. So my work is going to equal the force cosine of the angle times my distance. So this will actually be force times distance cosine of the angle. Just to give us a different way of looking at it. And that gives me the amount of work. Let's also look at the units. I have forces in newtons. This is in the meters. Cosine is a ratio, so it has no units. So I'm going to be in Newton meters, and we're going to define this as a joule. So my units per Newton meters is a joule. And that does remind me there is a quiz out there. There is a quiz. But this gives me a dot product associated with the work. So we can calculate the work done. By a 50 Newton force. So if we go ahead and give this a 50 Newton force, our angle is 30 degrees, and we're going to go over a distance of 10 meters. The work that's going to be done is just going to equal 50 times 10 times the cosine of 30 degrees, which is going to give us 500 times the cosine of 30 degrees, gives us Newton meters, which gives us 433 joules. But we're gonna turn this problem up on its head a little bit. So I have an ore bucket. And my ore bucket has a weight of 100 newtons. All right, my ore bucket has a weight of 100 newtons. We're bringing it up a distance of 5 meters out of the hole. So let's look at this problem just a little bit. Because one of the things that we know is my ore bucket has a weight of 100 newtons. We know we have tension in the rope. And at equilibrium, we know what that tension is. That tension is going to equal 100 newtons. But I can pull over here with my tension of 100 newtons. And all I want to do is keep the rope taut. And I can move this 100 meters or 5 meters. And the work that I did here has to equal the work that I did here. So we know what the work is because I'm in a straight line. My cosine of 0 is 1. My work is going to be 100 newtons times my 5 meters. And guess what? Same thing here. 100 newtons times my 5 meters. This is going to give me 500 joules. Now, this gets us into the definition of power. Because what happened when we were doing the steam engine was trying to figure out how many horsepower, if I used a mine pony, how much better did the engine do than the mine pony. So we defined power as work divided by time. Or we've already got that definition for energy, and we can say energy per unit of time, because work or energy is the ability to do work, but really when we're dealing with power, we want to know about work. So we have that, and this is going to be in joule seconds. And that's going to give us what we call a watt in the SI system, or we can look at it in terms of horsepower as well. But power is just defined as work divided by time and energy divided by time. And this gives us our definition because it goes back to the mine ponies. But we can do a couple of other things with this idea. This also gives us the idea of a couple of tools. So tool number 1. I have a lever. And I have a big rock here. And my rock is going to weigh 50 newtons. And I want to lift the rock 1 meter. Okay? I want to lift the rock 1 meter. I'm going to have to apply a force on this end of my lever in order to lift my rock 1 meter. But if I do this and I got a big lever here, and I'm going to use my lever here to be 2 meters, the work on this side has to equal the work on that side. Well, to do that, I've got a force of 50 newtons times 1 meter is got to equal whatever force I have to apply times my 2 meters. Those two things have to equal. So the force that I have to apply is going to be 25 newtons. So my lever gives me a bang for my buck. And one of the things that you notice is we've lost our vector aspect of the system. So that's one tool that we have. We have another tool. I have a ramp. All right, I have a ramp. The length of this ramp, we're going to say, is 0.75 meters. No, we want better. We want more than that. We want, we're going to say this is 1.5 meters, and this height here is 0.75 meters. I'm going to take a big mass. I'm going to take a big weight. And we're going to go ahead and do the same one. We're going to use 50 newtons. I'm going to make it so everybody knows that that's 50 newtons. And if I slide it up the ramp, the amount of work over here is the same amount of work as over here. And at the end, I'm going to be 0.75 meters up. So I'm going to have my 50 newtons at 0.75 is going to equal whatever force that I have to apply over 1.5. So my force is going to be 50.75 divided by 1.5. That should be the same thing I just did. I didn't get really fun on numbers, but we're going to go ahead and multiply it out just to make it life all good. Guess what? I only have to do 25 newtons. So my ramp and my lever all come from the fact that I've got conservation between these two systems. This side has got to equal that side. This side has got to equal that side. So we're about to define something. Go back to this. So I have the weight of my bucket. It's 100 newtons, and I've raised it 5 meters. And what happens if I cut the rope? This is going to fall back down. So by putting work into the system, so I put work into the system, I can store that work. I can store that work, and that stored work is potential energy. Now, our book is going to use the letter U for potential energy. I like to go ahead and continue to use the letters PE for potential energy because to me that makes a little bit more sense. So that I can talk about what's happening. All right, so my potential energy. is in there. So let's look at potential energy. So I'm going to take a ball and I'm going to lift it up 3 meters. It has a weight, mg. We're going to do 0.25 kilograms. Gives us 2.45 newtons. And we move this up to the top here. This is going to be our force times our distance, cosine of the angle, but our cosine of the angle is equal to 1. And now I've got something that's mgv, but in this case, our d is equal to h. This is going to give me mgh, and we're going to define this as our gravitational potential energy. Our gravitational potential energy. So we start to have the idea that work is going to be equal to energy. And this starts to give us our idea of the work energy theorem. Because energy is conserved. Energy is conserved. Now, we get a little funky here, right? We get a little funky. Because most of us have taken chemistry. We also talk about this idea of kinetic energy. And I'm going to use the Ke to represent kinetic energy. And our kinetic energy, which we've seen probably in chemistry, is 1/2 the mass times velocity squared. Or we can define work as our change in kinetic energy. Okay. And define work as our change in kinetic energy. So there are times that we can look at work as a change in potential energy. There are times that we can look at work as a change in kinetic energy. Then there's times that we can look at work as a change in all our energies. And we can utilize that to our advantage. Because if we think about what energy is going on, or thinking about energy, let's think about the types of energy that we come into encounter with. So if I'm looking at types of energy, we can have potential energy, we can have kinetic energy, we can have heat, we can have light, sound, electrical, and we can go on and on. Now, the thing about this is if I take an object and I let it fall, when it hits the ground, you might see a spark. You certainly hear sound. And we probably generate a little bit of heat. And depending on how far this falls, we probably generate heat due to friction. And this is where Mother Nature's not fair. Mother Nature is not fair. Because if we take a ball up and we bring it up here and we let it fall down, we wanted to have stored the energy. And we'd like to get it all back out. And we've seen this a lot. Think about this. Have a water wheel. My wheel, right? Water comes flowing into the stream, causes my wheel to turn. I'm using the potential energy of the water to rotate my wheel, which is in turn turning a shaft, which is allowing me to do physical work. But we also know some other things that happen. It would be nice to be able to use all of this potential energy and convert it into this physical work, but we know that friction is going to cause this to heat up and I'm going to lose a little bit. So my total energy, when I'm looking at these systems, is going to equal my kinetic energy, my potential energy, plus energy that we call non-conservative. And this non-conservative in the whole scheme of things, all energy is conserved, but I just can't get work out of that. I'm going to lose that to the environment. I'm going to lose that to heat. I'm going to lose that to friction. I'm going to lose that to drag. I'm going to lose that to a lot of different things, and I'm just not going to be able to get work out of it. So we get this idea of total energy conservation, and we can use it to our advantage, but I have to worry about, sometimes I've got non-conservative. And luckily for us, on a lot of the problems that we're about to work, we don't necessarily have to worry about it, but you do want to worry about it. I encourage you to go in and look at the pile driver problem that I go in and define all of this type of energy and energy conservation and looking at the work through that problem, but this gives you a little bit different approach as to how to come at it from conservation of energy. So let's look at what we have so far. So we've got potential energy is going to be defined as mgh. And this is our gravitational potential energy. Kinetic energy is defined as 1/2 mv squared. We have work is equal to the dot product of these things, which gives me my scalar product, which gives me that. Now I can also use Hooke's law, which we saw earlier, that force is equal to, or the work due to a spring, work due to a spring is 1/2 kx squared. So I've got my potential energy, my kinetic energy, my work due to a spring, I have work, and we have conservation theorems. That's going to help us out. So let's look at a problem here. All right, I have an object. We're going to drop it from the height of the building. Okay. We're gonna say my building is 50 meters tall. And I want to know the speed at which it hits the ground. All right. Well, we know our initial velocity is equal to 0. We want to know what our final velocity is equal to. We have a change in height of 50 meters. And we don't know time. Okay, but we do know the acceleration due to gravity is 9.81 meters per second squared. So we can use our equations, right? I get V final squared is equal to V initial squared minus 2GH. But this, my change in H is going to be negative, so I'm going to get, or this one is 0, so I got this. So if I get V final squared is equal to negative 2G negative H. And I get V final is equal to 2GH square root. So we've been doing those problems for a while. But let's do it looking at energy. We start out with potential energy at the top has to equal the kinetic energy at the bottom. Okay, potential energy at the top is mgh. Kinetic energy at the bottom is 1/2 mv squared. Mass becomes irrelevant. I get 2GH square root is equal to the velocity. I get the same thing. I get the same thing. That's a pretty cool result. Totally cool result. So let's take a problem like this. We're going to say that this is 3 meters. We're going to take an object to the top of the slide. We're going to give it a mass of 0.5 kilograms. All right. We're going to say this distance here is going to be 1 meter. We want to know how far that distance that ball is going to travel at the end of the table. Okay. Well, let's look at this part. The work done to get the ball up there is going to be 0.5 kilograms times 9.81 meters per second squared times 3 meters. So you get 0.5 times 9.81 times 3. I did 14.7 joules of work. Well, the potential energy at the top has got to equal the total energy of the system. And the total energy of the system here is equal to the sum of the potential energy plus the kinetic energy. Well, my potential energy here is going to be mgh, and my kinetic energy is 1/2 mv squared. But it turns out that this at the top, I only have potential energy. I can put the total energy or the kinetic energy at the top. This is going to be 0. We just did mgh, which we found out was 14.7 joules. Well, this mgh is going to be 0.5 kilograms, 9.81 meters per second squared. But I'm only multiplying it by 1 meter now. And this is going to be 4.9. So now I've got the total energy of the system. Was my potential energy at the top, which was 14.7 joules, is now equal to 4.9 joules plus 1/2 mv squared. So I get my 14.7 minus my 4.9 is equal to my 0.5 divided by 2 v squared. Gives me 9.8 times 2 divided by 0.5 is equal to v squared. Gives me 39.2. V is equal to 6.26 meters per second squared. And now we know the velocity at which our ball is coming off of the top. Well, we need to know this time that it takes it to fall 1 meter. So I know what my y velocity, my initial y velocity is 0 because this is only in the x direction on this slide. I know my height is equal to 1 meter. So I'm going to get my change in y is equal to v times time minus 1/2 gt squared. So I get minus 1 is equal to 1 minus 1/2 gt squared. T squared is equal to 2 divided by g, which gives me T is equal to 0.45 seconds. And now x is equal to vx times t. So I have 6.26 meters per second. Sorry. Times 0.45 seconds. Gives me 2.83 meters. So we can do a complicated problem with a little simpler math because we can use our conservation of energy principles to help us out. And then we can add in spring problems as well. Okay, we've gone a little long today, so, I'll stop recording here.